This video is part of an online course of Calculus 1 and I'm going to talk about instantaneous velocity. Basically, I wanted to find the velocity at a single moment of time. What is the strategy for it? Is this. We're going to consider average velocity. And you know that for average velocity, I need 2 points, two distinct times, and then we're gonna have the displacement over change in time. This gives me the average velocity. But if we consider average velocity over smaller and smaller intervals, over smaller and smaller intervals of time, then we can get the instantaneous velocity. Let's look at the graph. So observation is this. Let me have a big graph for this. This is time, this is y, and then let's have this one as s of t. S of t is the position at the time t. So assume that we have a moving object. S of t is the position of that. Okay. Then we have, for example, this is the time a, and assume that this is the time b, for example. Okay, let me move this one a little bit down, and we're gonna see that as b gets closer and closer to a, as b gets closer and closer, and closer to a, the point b and s of b, which is where? Which is here. This point is b and s of b, right? Gets closer and closer, closer to the point a and s of a, right? Where is the point a and s of a? Is right there. This is the point a and s of a. A and s of a, s of a. This is this point, okay? And something else. So as b is getting closer to a, if b is moving this way, this point is getting closer and closer to this point, right? And something else that is nice to notice is this one. Let me just move the graph in here. I'm gonna also move this one in here so that I have more space to write. As b gets closer and closer to a, the slope of the secant line, what do I mean by secant line? I mean this line in here. There's a line that is passing through these 2 points. This is a secant line. Let me just move this one a little bit down. Okay, so this is the secant line actually that is passing through the point b and s of b and af and s of a. Okay, so the slope of this line is gonna change. How? The slope of the secant line get closer to the slope of the, let's see, so let's get a, actually b to be this point that is closer to a. Okay, Then the secant line would be, see, this line, right? If B instead of here would be here, the secant line would be this. Now let's B to be a little bit more closer. Then the secant line would be right there. You see, the secant line is first right there, then here, then the blue line. And what do you think? This green line here is actually the tangent line at the point A and S of A. Okay, and as you see, if B is getting closer to A, the slope of the tangent line of the secant line is getting closer to the slope of the tangent line. You see, let me have one more B here, and then you will see. You see, if B is here, then the secant line would be right there, right? You see, the slope is getting very, very close to the green line, which is the tangent line, right? So to the slope of the tangent line at the point A and S of A. Okay? And so based on this fact, I can define the instantaneous velocity. So definition: the instantaneous velocity at the time t equals to a is the slope of the tangent line at A and S of A. Okay, so average velocity was the slope of the secant line between the point A and B, but for instantaneous velocity, A should be exactly B. So let's move B to A, and as I move B to A, then the average velocity is getting the instantaneous velocity, and the slope of the secant line would be closer and closer to the slope of the tangent line. Okay, so now the problem is this. I have a problem now, which is that we only know A of S of A. And we know that this is on the tangent line. We usually need 2 points to calculate the slope, like this slope, right? So that is actually something that we need to figure out later on in more details later on when we talk about derivatives and all these things. But let's look at the instantaneous velocity for now. As an example, let S of t to be t squared, and A is equal to 1, and B is another time that is greater than A. Then we know that we have 1, and then this is B, and we know that B is getting closer and closer to 1, right? So let me graph it first. So this is t, this is y, then I have, the parabola Let me have a nicer parabola in here. There you go. So this is y equals to t squared. At the time 1, I'm here. Let's have the time 1. So at the time 1, I'm at the position 1. So the point 1, 1 is in this. And then let me graph the tangent line. Is just because, there you go. I need to figure out the slope of the tangent line, right? And I know that the slope of the tangent line is basically the instantaneous velocity, okay? And what is the procedure? We said that we need to calculate the average velocity first, which is equal to what? Which is equal to the position at the second point, and the second point is B, minus the position at the first point, which is 1, over the change in time, okay? So the position at the point B would be B squared minus position at the point 1 would be plug in 1, which would be 1 squared, and then the change in time, B minus 1. Okay, so now let me just simplify that. I get what? I get B minus 1 on top times B plus 1, right? Because if you distribute B minus 1 into here, you get B squared minus 1 squared, divided by B minus 1. I can cancel out these two and I get B plus 1. Okay, so the average velocity based on the point would be B plus 1. Let's plug in some B's to get the idea. So I have what? I have different B's, and then this is the average velocity between time 1 and time B. Okay, if B is 1, okay, it would be exactly at this point, but it would be 1 minus 1. That's why I don't need 1 in here. Let me change it to 1.1. So somewhere in here, 1.1. That is close to 1, but it's not exactly 1. So at 1.1, just plug it into the average velocity, calculate that, and you get 2.1. Now let's get closer. I'm gonna change to some point in here, which is 1.01. Okay, so 1.01, calculate the average velocity, it would be 2.01. Okay, now let's get closer to 1.001. Okay, plug it in there, calculate that, you see you get 2.001. If it is even closer, I get this. So it looks like it's getting closer to 2. You see, it starts at 2.1, so it's getting 2.01, 2.001, 2.0001. So it looks like it's getting close to 2. Okay, but we need to be certain about this. Okay, so we can say that, so as B gets closer to 1, B plus 1, which is basically my average velocity, so the average velocity gets closer to 2. So we can say that the instantaneous velocity, or basically the slope of the tangent line, to the graph y equals to t squared at the point 1, 1 is equal to 2. Okay, and let me write it in here so that we say that the instantaneous velocity is equal to 2. Okay, but we need to calculate that. So that was the idea. Our goal is to develop this idea in general, and when we develop it in general, it has a name which is called limit. So I can say that as a note, the process of letting t, or basically x, approach to a point A in an expression, our expression here was just position function t squared. It's called taking a limit. Taking a limit. Okay, so on this question we basically take the limit of this function when the time t approaches to the point 1. We took the limit, and since our function was the position function, we got the instantaneous velocity. We're gonna talk about the limit in chapter 2, and that was the idea of the limit.